Okay, I had a student pop in. I've listed the variables here from our word problem. And the question asks, determine the force acting on Logan's body. So my impulse is equal to my change in momentum. My impulse is force times time. My momentum is my final momentum minus my initial momentum. So when I break out my equation like this, the only thing I don't have in this equation is my force, which is what we're looking for, determine the force acting on the body. So if we want to rearrange our equation to have force by itself, it would look like this. Force is going to be equal to my mass times my final velocity, which is 0. So this is just going to cancel out. Minus my initial velocity, or my mass, times my initial velocity, divided by my time. So my force is going to be negative here, and hopefully you are comfortable with this idea. We have actually a change in energy here. We went from a higher energy to a lower energy, so there's work being done on this player, and it's negative work because when I change in energy, I'm going from higher energy to lower energy. So let's see what that gives us. Negative 3,515 newtons. It's quite a bit of force. If Logan hit the concrete wall at the same speed, his momentum would have been reduced to 0 in 0.008 seconds. Determine what force his body would have been for such an abrupt collision. So this is essentially asking the same thing, except for our time has gone down. We had a higher time, and now we have a lower time. If you look at this part here, my force and my time, this part of my equation doesn't change. I still am starting with ending with the same momentum of 0, starting with the same momentum of whatever this was multiplied together. But now that my time is smaller, my force must go up. So I'm looking for a force that is greater than this. So this is part A. Part B, you'd set it up the same way, except for we would substitute our time, our new time, in the equation instead. So our force would be equal to, we still have no final momentum, our initial momentum divided by our new time, giving us, I can tell it's going to be really big. Newtons. All right. There we go. Let's see. These are all very similar. Let's do 13. And then we'll call it a day. I don't know that we need 2 days for this. Okay. So walrus has a mass, this is 13, of 1.1 times 10 to the third power. I do not like working in scientific notation, so I'm going to convert that. 1, 1. So I've moved my decimal place over 3 places to get rid of my times 10. With a speed of 9.7 meters per second. Suppose the walrus starts from rest and takes 19 seconds, so my time will be 19 seconds, to reach a velocity of 9.7 meters east. Oh. All right, this is not what I was expecting. Okay. So, excuse me here, my final velocity is going to be the 9.7, and my initial velocity, because it's starting from rest, is going to be 0. The net force acting on the walrus. So my force times time is equal to my change in momentum. My initial momentum is 0, so I can cross this off. Also, this is another one where we have a change in energy. Since we're starting from rest and we're increasing our energy, we're going to have positive work being done on this walrus. Okay, so this is what our equation looks like. We're looking for our force. I'm going to round. All right. Try the rest. Let me know if you have any questions.